So the purpose of this video is really to review Coulomb's law, but it's going to be a little different from the other video that I made on Coulomb's law. So the other one went over really like how to use this equation in order to solve for a missing electrostatic force, this F sub E over here. It went over how to solve for one of these missing charges if we don't know what the values of one of those things are, or how to solve this equation for a missing distance between two charges. But I want to spend most of the time in this video just sort of going over the concepts and patterns that arise from this equation that you all have been observing in your breakout groups. So I kind of want to hope to bridge the gap between this complicated looking equation and the things that you all have been seeing in your breakout groups so far. So that being said, I want to take a second to highlight some of those things that you all have been noticing in your breakout groups. Some really, really specific, detailed, key observations that you all have been picking up on just by being given the really vague task. I think I just said to like play around with the simulation basically and record what you all notice. So here, the farther a person is, the lesser the force. That's a really important thing, getting at this distance on an object or distance between objects affecting that electrostatic force. I'll show that in a second. We'll go over the relationship between those two forces. So the thing that I like about this sort of list of observations that I want to lift up is the fact that it talks a lot about like both forces or both charges or things like that, and the relationship between those two. I want to highlight that idea. And then the fact that if the charges are the same, then they repel each other, and if they're the opposite, then they attract each other. That's something that we all sort of intuitively have heard before. Opposites attract, like charges repel, maybe from even chemistry. But I want to highlight that observation as well. And then this other one in the same paper, when the charges are neutral, there's no force at all. So let's take a second. Let's come into not that simulation, but this one that you all have gotten a chance to sort of play with. And on the side, I want to still show our Coulomb's law equation over there, so that we can still draw some like similarities between those two. So, if you remember, a lot of people actually wrote about how when we move these charges farther apart, you can tell that the forces are getting smaller. You can tell that by two ways. This number is going down for the force on Q1 by Q2. That number will get smaller as we get farther and farther away. And then, just like in our free body diagrams, the weaker that those forces get, the shorter these arrows or these vectors, as we'll continue to sort of reinforce, these vectors get shorter as the forces get weaker, as we get farther away. So we know that as we increase the distance between these two objects, as they get farther apart, the force gets weaker. And conversely, if I move them closer, those forces get stronger, and these vectors get a little bit longer. Now, the other thing that people wrote about, the other thing that I wanted to lift up is that mentioning of both forces. So you'll notice that as I move these charges around, I can move either of them around. These forces always change together. So it's not that the forces are constant, but they are constantly changing together, in step with each other. Right? As soon as I move this one, now this force has gone down to 179.751. And this force has gone down also to 179.751. They're always the same thing no matter what I do. And we'll talk more later when we get into our like Newton's laws part of the year, that this is a Newton's third law force pair. But for now, it's important for us to note that those forces acting on one charge by another are always equal. And it doesn't even matter if one of these charges is, let's say, much bigger. Let's say I make one of those charges 10 microcoulombs and this one 2 microcoulombs, still the forces that they exert on each other are still always equal. Their charges don't need to be equal for the forces acting on them to be equal, because they're exerting those forces on each other. They exert equal and opposite forces on each other. Now, the other thing that we noted was that if these charges are the same sign, right, if they're both positive like I have them now, I'll move them closer to show this better, then they repel each other. Then our object on the left is pushed to the left, our object on the right is pushed to the right, as long as they're both positive. They don't have to be the same number, so like this one, this charge 2 here doesn't have to be 10 microcoulombs the same as charge 1, as long as they're the same sign, as long as they're both positive, or if they're both negative, then they will repel each other. One other important thing to note In the same way, let's say I change this -8 microcoulombs to +8. Then you'll notice that our direction has changed. We have one negative charge, one positive charge. Since those are oppositely charged objects, they are now attracted to each other. The object on the left is pushed or pulled to the right towards this charged object, and the object on the right is pulled to the left towards this charged object. Again, the forces are the same as each other, but they're now moving towards each other instead of away. And I just want to highlight one other thing that you might have noticed a second ago, but that I didn't say anything about. When I switch from +8 to -8, notice what happens to this force. Right now it's 293.471. And again, now still 293.471, but the direction changed, right? So the value of this charge, how imbalanced it is between electrons and protons, how charged it is, will determine how strong the force is. But the relative signs, positive or negative, between these charges will determine the direction of that force. So when this charge was positive, it was this 293.471 towards that one, since they were opposite charges. And when this became negative, now they are repelling each other, but with equal strength, since I changed just from +8 to -8. Just highlight that a couple more times. Only the direction is changing if we go from +8 to -8. So that's another important thing. Now, in terms of bridging the gap between our our observations and what we see in that equation, in Coulomb's law, we see distance, that r, in the denominator. So that's why it kind of makes sense that as we move these farther apart, as that denominator, the r, gets bigger, the electrostatic force goes down. And when our denominator gets smaller, the force goes up. On the other hand, if I change the charge, right, our charges Q1 and Q2 are in the numerator, as they get bigger, and I'm just going to change charge 2 here, as it gets farther from 0, you'll notice that force go up. And in fact, that's what happens, because our charges are in the numerator of that equation. Now, there were some good questions about, like, on the exit ticket, what I mean when I say when a charge increases or decreases. Really what I mean is getting closer or farther from 0, because we know if we have a charge of 3, and you think about like -6 or -7, maybe -7 is smaller because like it's more negative or something, but no, -7 has a stronger force. A larger charge will generate a stronger force than just 3 microcoulombs, because that is farther from 0. So I think maybe the better way, that was brought up I think in class 5, the better way to think about like increasing charge or bigger charge might be just, is that charge getting farther from 0 or farther from being balanced between those electrons and protons? Now, the last thing I want to point out to you all, in the equation, a lot of people asked on the homework about like, what does it mean if I get a negative force in Coulomb's law over here? Like, what does it mean if I see -8 newtons as the force between two charged objects? Which is a really good question. What that negative charge, or excuse me, what that negative answer for a force would mean is just that there's an attractive force between these two objects. And the reason for that, by our equation, is that if we have a negative multiplied by a positive, then our answer is going to be negative. So as long as these two charges are different, a positive and negative, as long as the signs of those charges are different, then we're going to get a negative for our force. On the other hand, if we have two negatives, when we do our Q1 times Q2, a negative times a negative is just going to give us a positive force. And obviously when we get a positive times a positive, then our answer is going to be positive for that force as well. So in Coulomb's law, the sort of sign convention there, and it's a little bit weird, it's a little different from how our sign convention will be for a lot of the year, but a positive force in this context means that those two objects are being repelled because they're the same sign. And a negative force would be showing that those two objects, those two charges, are attracting to each other. So again, if you need a review of sort of the math of Coulomb's law, you should look at the other Coulomb's law video, but this was really just meant to be a conceptual sort of summation of some of those observations that you all made, so that going forward you can sort of bridge that gap on your own between the equation and between your observations and between those concepts.